morning. Welcome back to the course Engineering Metrology, and I am taking statistics in metrology part in this course. So, this lecture will continue the probability distributions, and I will discuss more on the normal distributions, some proportions, and chi-square distribution I will introduce and try to put some light on the numericals on these as well. Now, contents will flow like this. First, I will just introduce the normal distribution, and I will discuss the normal distribution in detail. Then I will see the how good of, I will put an or I will pick an example to explain that how good is this data, or how good is not this data, how good is normal distribution in real life. Then what is standard normal distribution, and I will discuss something about proportions, and I will try to solve an example on this. Then I will discuss the chi-square distributions. Chi-square distributions are actually distributions of variance, okay, or standard deviations. So, then as I have told you that sometimes data outlier is there, in the data some outliers are there. Data outlier detection, there is a rule, Chevenet's rule on this. So, we will discuss that. First, introduction. What is normal distribution? Normal distribution sometimes is also referred as Gaussian distribution, because Gauss came up with distribution, is the most common continuous distribution used in statistics. The normal distribution is vitally important in statistics for three main reasons. Number one, numerous continuous variables common in business have distribution that closely resemble the normal distribution. So, normal distribution can be fit into the maximum of the measurements that we take, to the heights, to weights. In metrology, in business, if I am talking the wages of the customers, the prices in the market for the specific products. Okay, the different distributions can happen, but I can call normal distribution as the mother of many distributions. However, there are many distributions like Weibull distribution. Weibull distribution is not a single distribution, it is a family of distribution. Similarly, normal distribution is also a family of distributions. So, normal distribution, the second reason here can be the normal distribution can be used to approximate the various discrete probability distributions. Now, there are various distributions like Poisson distribution, binomial distribution, Weibull distribution, Rayleigh distributions, and uniform distributions. We can have normal approximation of many distributions. What if we try to plot our data on normal distribution? Okay, it can be skewed, it can have some courtesies, but how well is if we consider our distribution to be normal, whatever the other distribution is, let me say log normal to be normal, or the Poisson distribution to be normal. As I said, when I increase the value of lambda in Poisson distribution in the previous lecture, it was approaching close to the normal distribution. So, normal distribution can be used in an approximation of various discrete and continuous distributions. So, various discrete probability distribution is an important point here, because discrete data is able to produce less powerful analysis. So, it is important here. So, normal distribution provides the basis for the classical statistical inference because of its relationship to center limit theorem. I did not discuss the center limit theorem. Center limit theorem is that there is a central value along which the other values lie. The true value is actually the actual value. This is a central value can be mean here, okay, along which the other values lie. This is center limit theorem. We need not to get into the details of this, but yes, normal distribution is actually obeying the center limit theorem in a very good way. So, these are the few reasons for which normal distribution is used. Now, what is normal distribution? As I discussed in the previous slide, normal distribution has PDF, this is equal to sigma under root 2 pi, and I took the standard variance out and it becomes standard deviation. It was sigma square before. This is another way to represent. Then e to the degree of minus 1 by 2 x minus mu by sigma whole square. We can note that the value of pi and e are known here. Pi is 3.141 and E is 2.718. So the only variables here are sigma and mu. Okay, so these are the two parameters, statistical parameters that need to be determined in normal distribution. If I draw the normal curve, the curve is symmetrical around the central line and it is asymptotic curve. I can put here the curve is asymptotic. By the word asymptotic, I mean that the curve or asymptote of a curve is a line such that the distance between the curve and the line approaches 0 as one or both of the x or y coordinates tends to infinity. When this tends to minus infinity and this tends to plus infinity, this distance tends to 0. Okay, this distance tends to 0. That means the curve is asymptotic here. Also, we can divide it into various parts based upon the standard deviation. I can put the value 0 here. Let me say the value 0 is here. This is minus 1 into standard deviation plus 1 into standard deviation. This distance is same from minus 1 to plus 1. I can even have minus 2 sigma, minus 3 sigma, plus 2 sigma, plus 3 sigma. Now, the area between minus 1 and plus 1 sigma is 68.2%. This area this is 68.2%, or I can even say it is 34.1% here and 34.1% on this side. Okay, this area. And in 2 sigma, like area between 2 sigma, that this is actually the beauty of the normal curve. Whatever the kind of data is, this probability, actually this area is actually the probability. This doesn't matter. This would always remain, we call it 68% between 1 sigma, then 95% between, this is 95%. If I color this total area, this is actually 13.6 here and 13.6 here, which adds to this 68.2. It is actually 95%, and within 3 sigma we have 99.7% of area. Okay, area. area. So, whatever is the value of mu or sigma, this area, this probability, okay, 68%, 95%, call it 99.7%. This is independent of the values of mu and sigma. So, that is why normal curve is most used in practical situations on the data that is having continuous distributions. So, this is the tabular form of the distribution. In this table, we are presenting the data, and if I see this value at 1.48, this is value at So, the probability at z less than equal to 1.48 is equal to 0.9306. Okay. Actually, if I write it, so here the probability 0 is less than equal to z is less than equal to 1.48. You can see 1.4 here and 0.08 here. This is equal to 0.9306. Now, this is the curve. You can see this area is here. This value is, oh, actually this is minus infinity here. I am so sorry, based upon this curve. This should be, it should be minus infinity. This is minus infinity to 0, then 0 to plus infinity. I have value 1.48 here. Okay, from minus infinity to 1.48, the value is 0.9306. What is z here? This is known as standard deviate. I will just put some more light on this when I will discuss standard normal distribution. So, this value 1 sigma, 2 sigma, 3 sigma, the value 1, 2 and 3, this is the value of the normal deviate, that is contributing to my the spread of the data, what spread we are trying to keep or what spread we are trying to look at. Okay. So, the curve or the table can be given, this tabular form can be given in two ways. This is one way we have complete data, another way can be it can be presented in this way as well sometimes. This illustration would also always be there, that will be presenting what kind of data do we have. So, if it is like this, that means that table represent from values from 0 to z. In this case, this value would be actually 0.9306 minus this area, this is 0.5, 50% on left side, 50% on right side. So, 50% minus 0.5, this is equal to 0.4306. So, when we see the normal curve and we need to see the normal table, we need to be careful what kind of table, what kind of data we have, what is the limit of the data, from where is the value starting, is it from minus infinity or is it from 0, we need to see this carefully. Okay. So, next is standard normal distribution. Our normal distributions can be converted into standard normal curve by subtracting the mean and dividing by the standard deviation. Now, this is my random variable x. If I subtract the mean from it and then divide it by standard deviation, I get my standard normal distribution. Now, actually somebody calculated all the integrals for the standard normal and put them in a table. So, we never have to integrate, like even better now computers are available to do the integration for the standard normal distribution. This z, this value z is known as normal deviate. Okay. This is our random variable, or we can just call it variable as well. This is mean, this is standard deviation. Standard normal distribution is used for the calculations. Now, how to find the probability? How to find the probability in the standard normal distribution? First, we just draw a bell curve and shade it in the area that is asked in the question. For instance, if this is my curve and I get this curve here and I need area, let me say they say calculate z that is greater than or equal to minus 0.5. Please be mindful here, the value of z is 0.5, it is not sigma. So, it is actually, if this is minus 2 sigma minus sigma, this is plus sigma plus 2 sigma plus 3 times standard deviations. So, it is asking the value of z greater than equal to minus 0.5, value of it is asking the probability, that is for the value of z greater than minus 0.5. I will just mark the value 0.5 sigma minus. Okay. Now, this is the line I need to mark here. I will shade the area. Now, I need this value. I will just do it taking some problems, taking some numerical problems. Now, that means we are looking for the probability for the value of z or z that is greater than minus 0.5, and we need to draw the vertical line at this, like I have drawn this vertical line here. Vertical line at this vertical line has to be drawn here. This vertical line, I will draw the vertical line here at the point where the value is required, and standard deviations from mean, and we shade everything that is greater than this number, that is we need this area, whatever the shaded area is, we need this value, what is this area, this area would be the probability. Now, we need to visit the normal probability distribution index and find a picture that looks like our graph, like we had this picture before. Yes, this is the kind of the picture that we had in our graph. The only difference is that the shaded area is on the left side. We can always take it. If it is minus 0.5, we can take the value at plus 0.5 as well. So, at plus 0.5, the value is 69.15. Okay, this is the value 69.15. Okay, I have made double circles over it. So, this value we will see. So, this for p greater than, for p of z greater than equal to minus 0.5, the value is 0.69 something, 0.6915, 0.6915. Okay, this is the way. Now, let us try to solve a numerical problem. Now, the question tells that we measured the length of an element, the measurement was normally distributed with a mean 727 mm and the standard deviation of 112 mm. What is the probability of a measurement being above 500? Now, let us note on the data, mean is equal to 527 and standard deviation is equal to 112. So, if I try to draw the curve for this, this is 527, okay. This is length in mm, length in millimeters. Okay, 527 here. Now, I will just draw a bell shaped curve here, okay, which is symmetrical central value here. So, he needs the value that is above 500. Now, x is equal to 500 here. Where above 500? 500 is somewhere here. Here we have 500. So, can we find this value? Let me shade this area here. I need this value. Okay. Now, the way to do this is, we know that standard normal deviate z or z is equal to x minus mu by sigma, which is equal to 500 minus 527 by 112. So, this comes down to minus 27 by 12, which is equal to minus 0.2411. Okay. Now, probability for the value of the random variable x greater than, it is not saying greater than, equal to, just greater than 500, this is same as probability for the value of z greater than what? I need to see the value of z here, minus 0.24, which is equal to, now where do we find this probability? We need to see the probability distribution table or the probability distribution area that we have. Let me go to my distribution table here. This is the probability distribution table. You can note one thing, I have intentionally put this table here for value for the 1.48, the value that we selected was 9.43, here the value is 0.43, okay, 0.436. So, I haven't put the curve here, which kind of table is it. So, I will draw two curves, please let me know which kind of table this is. Is it this table or this table? Okay, please take a few seconds to see whether case 1 or case 2, which kind of table is this? Yes, I think you got it right. It is not the case 1, it is the case 2. So, this is not selected, this is selected because the value is only on the right hand side from 0. Okay, it was 0.9306, it was 0.9306 had it been this table, okay, this curve here. So, it is case 2 here. So, we need the value of minus 0.24. For 0.24, let me see the value 0.2. 0.2 is here and 0.2 and 4. Okay. So, I have got the value 0.948, this value is there, 0.948. But what do we need in the question? We need this complete area. Now, this area from 500 to 527, actually from 500 to 527, the area is, so this is 0.0948. So, the probability for x greater than 500 would be equal to the other half of the area, that is 0.5 plus this 0.0948. So, this is equal to 0.5948. Okay. So, this probability for the measurement being above 500 is equal to 0.5948, that is, if I say percent, it is 59.48% of chances for the value to be above 500 mm. This is my inference here. Okay. So, let me take another question here. A length of horizontal bar is normally distributed with mean 266 mm and standard deviation of 16 mm. What proportion of the measurement will last between 240 and 270 mm? So, I just picked one value greater than 500 in the first case, just one value, and try to solve that. Now, I am taking an interval 240 to 270. But within this interval, how to calculate? Now, I will follow the same steps. First, put the data here. The mu mean is 266 mm and value of standard deviation is 16 mm. So, let me draw the normal curve here with mean is equal to 266. We need to see the value between 240 and 270. 240 would be little on this side, values between 240 and 260. Okay. Now, again the value of normal deviate z is equal to 240 minus 266. I am using the same formula, x minus mu by sigma, z is equal to by 16, which is equal to minus 1.625, the value of normal deviate. And for value of z, for 270, it is 270 minus 266 by 16, 4 by 16 is 0.25. Okay, this is plus. So, I need the probability from 240 is less than x is less than 270, which is equal to probability for the value of the normal deviate from minus 1.6. I have only about up to 2 places of decimal, so I will round it off to 1.63 is less than z is less than 0.25. Okay. Now, there are ways to deal with this. One way is I calculate this area separately and this area separately and then sum them up. For that, I would have to separately see the values for 1.63 and 0.25, like considering that area on the only one side is required, and sum them up. Okay. Another way here is I will just put this as in a line here. I will put this in a line. I will see this probability is 0 and this probability is 0.25 and this probability is minus 1.63. Okay. What will that make me to do? I am just interested in this value. This value. So, what can I do? If I subtract from this value 0.25 the value minus 1.63, I can get this thing. So, one way to do this is I can take it as this is equal to probability for z less than 0.25, okay, minus probability for z less than minus 1.63. So, this whole area is subtracted from this. You got my point? I am having this curve here. I just need this area. So, what I will do? I will pick this whole area on the left hand side, this whole area left hand side, that is from 0.25, and I will subtract this area from it, from the whole red area, from this whole red area. Okay, I am subtracting this blue area. Okay, this is one way to do it. So let me follow this way. So here the value of z at 0.25, I need to see the value, and 1.63, 0.25. The value is 0.0987. So 0.5 would be added here. This plus 0.5 in my case, because I need the whole probability. Then for minus 1.63, 1.6 is here, 1.6 and 1.63, it is 4484, and I need the other side of value. I'll actually subtract 0.5 from this. Okay, 4484 and 0.987, 0.0987. So this is equal to, I'll put it in a bracket separately, 0.5 plus 0.0987 minus, so this value, next value is 0.4484, but this would be subtracted from 0.5. So I think you can now make it clear that why I am adding 0.5 to this, because I need in the case 2 here, like not case 2, actually figure number 2, this is figure number 1, okay, this is figure number 2. In figure number 2 here, the red area, red shaded area, we need to add 0.5 here, we need to add this 0.5 here in the red area, and for the blue shaded area, only this area is required, blue shaded one, I need to subtract this, subtract the value that I have got from 0.5. So this is 0.5987 minus 0.6150, 0.0516. This is equal to 1745, 0.5. Now this means that 54.7% of chances that the values lie between 240 mm and 270 mm. So I think with these two examples, the normal distribution, how do we use normal distribution, and normal distribution is actually population distribution, how from the information of the sample we can calculate the probabilities, we can calculate the points at between which our values lie, or above or below which our value or measurement could lie. Okay. So next I will try to discuss the skewness in normal distribution. Sometimes, as I discussed with distributions, I had been telling that the distribution is skewed towards right. What is this skewness? There can be two kinds of skewnesses here. Data can be left skewed or right skewed. Generally, I have found in my past that the students generally consider the peakness of the curve as the skewness. They think that the curve is peaked toward the right, they call it right skewed. Generally, they think that. But the skewness is attributed to the tail of the curve. The tail, if the tail is towards left, this is known as left skewed data, or data or distribution, whatever you call. This is right skewed. Distribution. Okay. So in left skewed data, this is also known as negatively skewed. Negatively skewed. This is positively skewed data. So the curves that we have been discussing, log normal, Poisson, those were right skewed, most of them. So what happens, what does this mean? It implies this is actually peak. Peak means this is mode. I'll call mode as MO. Mode remains at the peak. Mode is the maximum frequency of some value. Mode remains at the peak, and with the mode, and I'll first talk about the right skewed distribution. I have median and mean here. This is median and this is, I'll call it ME, mean, just giving a notation here. Median, I'll call it ME, mean. Okay. So an example here can be put as like, for instance, if I give test to the students, if the test is too easy, most of the students would be getting the marks higher. So the data would be, you can just consider, would it be a left skewed or right skewed? Most of the students would be getting marks higher, more than the what is average. Okay, data would be left skewed in that case. So this is easy test, and this is a tough test. Tough test means this is my mean, and most of the students are having marks less than mean, less than this mean, and most of the students having marks greater than this mean, in this direction, in this direction. This can be an example to just to explain the skewness. Okay, skewness can also, or skewness or the coefficient of skewness can also be quantified, that can be calculated using some relation. The very commonly used method here is Pearson coefficient of skewness. Pearson coefficient of skewness. This is also known as mode coefficient of, or Pearson mode skewness. Pearson mode skewness implies that skewness coefficient, we call it, I'll just donate it skewness SK, and I'll put P here as Pearson coefficient of skewness. This is actually equal to the difference from the mode, difference from the mode of mean. Actually I put mean M here, I can put x bar here as well. This is mean x bar, this divided by standard deviation. This can also be taken to the alternative formula, can be the median or a Pearson median skewness, Pearson mode skewness, because we know that x bar minus mode is generally taken as 3 times of x bar minus median. So this skewness coefficient can be written as 3 times of x bar minus median by sigma. So I am more interested in median because we are talking about the values those lies to left or right in my curve. So the central tendency or the location point here is the median. I'll just try to draw the box and whisker plot as well to explain the skewness further. First let me try to put the various methods to calculate the skewness. Okay, for the box and whisker plot, I can see the values here. Here actually mode is less than median is less than mean. So if I draw a box and whisker plot here, actually in normal distribution, in a regular normal distribution, we have all these values aligning at this point. It is x bar and mode and median in a symmetrical normal distribution, and the box plot for this kind of distribution would be very symmetrical. Okay, this will be very symmetrical like this. So this is my Q1, quartile 1, quartile 2 and quartile 3. But in this case, because mode is less than median is less than x bar, the data, we can see that most of the data would be lying towards the right side. Okay. So, here it will be somewhat like this. So, that means it is positively skewed and most of the data is on this side, and this is my median, this is my median, this is my Q1 and this is my Q3, and in this case it is the other way around. In this case, this is my Q1, this is my median and this is my Q3. We can also see that this is a long whisker here on the right hand side, because this line is some point will be at very far state here, and the points are near here. The whisker is very small here. In this case, in case of positively skewed data, the whisker here at this point, some like the end point would be somewhat here. Okay. So, I can call it start and some. So, this is a long whisker here. In this case, the long whisker is on this direction. So, this is another way to represent this skewness. So, Pearson coefficient of skewness is one criteria. There are some other criteria like quantile or quartile coefficient. Okay, based upon this also I can put skewness coefficient here. Then we have quartile coefficient. Quartile coefficient of skewness. Quartile coefficient of skewness, I can say S skewness due to quartiles. This is equal to Q3 minus median minus Q1 over Q3 minus Q1. Now, when we will have the skewness coefficient, also we can have the percentile skewness coefficient. Percentile skewness coefficient. Then skewness percentile can be something, if I take, let me say from 90%, 95%, it can be P 95 minus median minus fifth percentile. Okay, then 95th percentile minus 5th percentile. I can pick any percentile, rather any quantile to find the coefficient of skewness. The thing is that I just need a coefficient. The coefficient would have a sign and a magnitude. Sign would represent whether it is negative or positively skewed, and the amplitude would represent the extent of skewness, how it is skewed. Is it highly skewed, or it is just moderately skewed or very lightly skewed? That can be determined. Okay, let me just pick some values and try to calculate this coefficient of skewness. I will just do some calculations here. Let me pick the value of standard deviation, mode and x bar. Okay, let me say if x bar, x bar is, let me say 50, or let me, okay, to make it simple I will say just x bar is equal to 10, and mode, or I will better should put median here. Median is equal to 12 and standard deviation is equal to 3. Now, skewness coefficient here would be coefficient of skewness, or Pearson coefficient of skewness, Pearson mode coefficient of skewness would be 3 times of x bar minus median divided by standard deviation. So, this value comes out to be minus 2. Now, there are two values here. Minus 2 implies it is negatively skewed. negatively, okay, and this is extent of skewness. Negatively skewed, like I said, in negatively skewed, here we have mean or x bar less than median and less than mode. We can see that x bar was less than median in this case. So, it is negatively skewed. This amplitude of skewness, there are different acceptability level for this. Amplitude of skewness 2 is actually too high. So, sometimes depending upon the application we can accept 2 as well sometimes, but in case of normal distribution the general value is less than 1. Okay, but depending upon the kind of data we have and the kind of distribution we are selecting for that, and we can just have the feel of the data, whether how is it skewed, to what extent the skewness has happened. So, we can also see this, we can just find the coefficient of skewness. So, we will meet in the next lecture, we will discuss the statistical parts in metrology further. Thank you.